Alright guys, welcome to Mutex locks for concurrent game programming. I uploaded this video kind of partially in celebration. I just hit 2,000 subscribers on YouTube, so you can kind of consider this video kind of like part of a thank you for all the subscribers I've had. A lot more interest in these programming tutorials than I initially thought there would be when I started them. I kind of just did them because a lot of my friends, used to like, when I would teach them stuff about how to code, and I guess I decided, maybe it'd be a good idea for me to try it on YouTube, and it seems to be working out pretty well, so thank you guys. Anyway, we're going to get started here. So this is kind of a sequel to my last threading video, which I didn't cover mutex locks, and I kind of felt like that was unforgivable. So this is kind of like level 2 of thread programming. I'm going to link the first video in the description. If you haven't watched that one first, I recommend watching that one first. But anyway, let's talk about mutex locks. So welcome to hell, bitch. I'm just kidding. When you do multi-threaded programming and you don't know about how to do this kind of programming, it can be like hell. So I want to keep you guys from that hell because, a lot of things can go wrong. So anyway, I love how I messed up the first slide off the bat. So anyway, when you have a single thread of execution, basically, if you have a single thread of execution accessing a resource, the way it might work is that you might have, a couple functions in your call stack trace, and one of those functions at some point will be accessing a resource, and it might look like function 3 is accessing the resource. In this slide presentation, I denote resources as a green box with a smiley face, meaning that the resource is happy and everything's fine, because in a single thread, there isn't a lot you can do to screw up a resource if it's been properly designed. So what happens if you have multiple threads of execution accessing a resource? Well, unless the resource is specifically deemed as thread safe, that's a word you'll hear a lot, thread safety and thread safety of classes and objects and resources. If the object or the resource is not considered thread safe, you can essentially break that resource by accessing it concurrently. And by concurrently, I mean at the same time for multiple threads. And that has to do with the internal state that many C++ objects, or just code objects in general, have to maintain to make sure that what they're doing doesn't get interrupted and essentially break the internal structure of that resource. But the important thing to keep in your mind from a high level is that resources that are not deemed thread safe cannot safely be accessed from two threads at the same time. That just can't be done. So what do you do to make a not thread safe resource suddenly thread safe? How do you do what you're trying to do here safely? When the first resource accesses it in function 3, it acquires what's called a mutex lock on the resource, such that when function 4 accesses it in the next thread, or in the same thread at the same time, it cannot go in to the resource until the first thread is finished with it and drops the lock. So that's a little confusing, and I'm going to try to explain it the best I can in one slide. So here's our resource, right? So let's assume in some thread, we'll call this thread red, signify it with the color red, we want to access this resource. Well, if this is a thread safe resource, what will happen when the resource is accessed is that the red thread will acquire a lock on the resource. As soon as that lock is acquired, essentially any other thread that tries to access that resource at the same time, and by same time I mean while red still has a lock, will be locked out. So essentially the blue thread now has to wait as long as it takes for the red thread to be using the resource and to essentially relinquish his lock on the resource. Once that happens, the red thread goes away as far as we're concerned, and so does the lock, and the blue thread is allowed in. And now the blue thread is allowed to acquire a lock on the resource, and so forth. So now if another yellow thread, while the blue thread wants to access this thing, it has to wait. So that's essentially mutex locks explained as simply as possible in one slide. And it has to do with acquiring locks and releasing locks. Things can go wrong, and I could explain them and go into a whole big computer science discussion about deadlocks and all that crap and consumer provider problems. But at the most fundamental level, this is really all you need to think about when you're starting out. And great, there's a fucking fire truck going by. Doing these videos is really fun when you live in the middle of a damn noisy city. Anyway, as I was saying, this is basically all you need to know when you're starting out and you're concerned about how to do thread safety. I've been able to solve some very complicated problems, and one of the things that inspired me to do this video was because I actually was able to solve quite a bit of complex concurrency problems in my latest project that I'm doing for work, simply by using proper thread safety implementations using mutex locks. So let me kind of drop this and start into an example here. So basically what I have here is a very, very simple single file C++ program that essentially calls a function called spawn threads, and what spawn threads does is creates 3 threads C++ style that run for 2, 1, and 500 2 seconds, 1 second, and 500 milliseconds each respectively. So basically thread A runs, gets its own thread ID, sleeps, and then quits. And so does B, sleeps for 1 second, quits, and thread C sleeps for 1 second and then quits. And then by simply declaring these 3 threads, they've been launched, and then immediately after on the main thread here, I wait for all 3 to be done by joining with them, and then that's the program. So if I run this, it'll take about 2 seconds to finish because all the threads are running at the same time. So how does this get us into a concurrency problem? So up here we have this set of thread IDs. This is essentially a low-level data structure, a C++ STL set, or we can think of it in this case as our shared resource. This is something we are going to attempt to share between all the threads. And the basic idea here is that we would like to store a set. This is a dumb example, I know, but it's something I could use to get this point across. So we would like to store a set of the finished thread IDs of the threads that have since finished. So how would we do that naively if we were just thinking and we weren't used to concurrency problems and race conditions and multi-threaded programming? Well, naively what one might do is simply say done threads, insert the thread ID, at the end of each thread. So we think that would do it, right? We'd be done, and at the end of this, we'd be able to print out done threads, and we would have all the threads, or we would have a set of 3 objects, and those 3 objects would be the thread IDs of the finished threads. Now let me explain why I'm not even going to run it. Essentially, this is completely wrong. So it's commonly known, and I'm going to tell you guys, that basically C++ data structures, set, list, map, all those things, are not thread safe. They are considered very low level, built into the C++ standard types, and they just simply are not thread safe. And they do that because most of the time people are assuming that they're going to access these things only from one thread, and a lot of unnecessary locking and unlocking can actually slow your program down. So by default, these things are not thread safe. So if I go to try to access these at the exact same time from 3 threads, what I'm doing essentially might work, and probably will because I'm splitting it across multiple seconds, but it's very dangerous. It's considered not thread safe. I could break the data structure completely, maybe cause the program to crash, lock up, freeze, or worse. And essentially, it's called a race condition. 2 things happening at the same time, depending upon the output, depending upon which order you access them, as a race condition. So what we're doing is bad. How do we fix it? So the whole point of this example is basically we are going to convert this set, or at least the usage of this set, into a thread-safe operation. So how do we do that? Well, first we need this mutex. So you can see up here I included mutex, which is a header file that gives me access to various locking mechanisms. And we're going to use those locking mechanisms to make sure that if any of these threads go to do anything with the done thread set at the same time, whoever acquires the lock first will win, and the other ones cannot access done threads until the other locks have been relinquished. So first we need our mutex lock itself. This basically just is mutex. Usually I name it after the object that it's locking on, the thread safe object. We will basically have a mutex that represents our single lock that can be acquired by any one of these 3 threads in any given order. Now in C++, the way this works is all you have to do is declare something called standard, which we're already in the standard namespace, lock guard. I have no idea if I spelled that right. So what we then do is basically we say lock guard mutex lock on done thread mutex, And this is in the same C++ style. When the destructor of this class is ran, the lock is essentially released. So the lock exists from the point we declare it until the point it goes out of scope down here. Just want to make sure this compiles. It does. Now that we basically have done this, we've essentially acquired the lock properly on A. Now we have to do this everywhere in every thread that we access done threads, even the main thread. So this is important. So basically I'm going to replace my not thread safe access of done threads with the thread safety of the lock. Then we're going to wait for the threads. Now down here we could safely access it without a lock simply because the threads are done. Before this we could not. What I'd like to do anyway is, just for good practice, use the lock even down here. So we lock the resource. Then we iterate through the resource. And in here we can actually print out our thread IDs safely because we know that we're in the middle of a lock. So if another thread was running while we were doing this, and we were curious about the current state of maybe which threads were done while other ones might not be, this would be a safe way to do it as well. And there you have it. Whoops. And there we go. We basically now have the printed out thread IDs of each of the threads that have finished. Now what's neat is if we wanted to do this maybe when some of them have been finished and other ones haven't, it's entirely possible that maybe I can just decide to sleep for a little bit longer than 1 second, and maybe we'd only get the ID of the first thread that was finished here. Oh, that's right, the one that's only 500 milliseconds finished. So we can see at the first snapshot, 2 threads have finished, but the one that takes 2 seconds hasn't, and then when we're completely done, we figure that all 3 have done. So the important thing to take away from this video, it is a little bit confusing, is that basically you cannot, if there's ever a resource that is considered not thread safe, you cannot call any methods on that resource at the very highest level, like a data structure for STL, without first acquiring a lock and then relinquishing the lock as soon as you can when you no longer are using that resource. What this does is serializes all the requests to that resource so that none of them can intertwine and screw up the individual resource. If I wanted to go further with this example, but I'd like to stop simply because I don't want this video to drag on like my videos usually do, what would make a little bit more sense and make this code a little bit more readable would actually be to convert this set class into basically, we could call it a thread set class, and then we could write our own insert methods and our own enumeration methods, and essentially wrap those around locks and wrap the whole class, and that way when we call insert from here, it would automatically have the lock stuff inside that insert method. So basically what we would do in that case is we would convert the set class to a thread safe wrapper or thread safe variant, and then that way you could safely call those methods. And that's what a lot of programmers do when they want to convert a class that might not have previously been thread safe to thread safe. A lot of times it's as simple as using mutexes in the proper places on the underlying resource that class wraps. Oh, 2,000 subscribers. None of them thoroughly confused the shit out of you guys. Thanks for watching, and that's the end of this one.